Here we go. We want to recap some of our limits, mostly graphical today. So we're really hitting on this graphical limit again. I want to recap the formal definition of the limit. I want to go graphical limits, and I want to look at how limits, how could they not exist, and then we'll hopefully we'll have time for section 2.1 secant tangent problem. It's a lot to do. Let's see how much we can get through. So make sure if I'm doing something too fast, you slow me down, because I just had 2 cups of coffee and 3 days of rest, so I might be going way too fast here. We want to look at that formal definition again, right? With Sketchpad. And that's a software program. I want you really to see what's happening with that, and technology makes it so much easier. We want to look at more graphical limits, but more important, when do limits fail to exist, right? And then we're going to do that secant tangent problem, which is 2.1. So I don't do things in order. I do them as I want to do them, because I'm ADD. I get a little bored following a book. I would hate it when my teacher would read out of the book. Oh my God, drove me crazy. I'm like, I could do that. What am I paying you for? And the book is a lot more formal, right? So the book is very super nerd. So, and again, I feel like it's my job to teach you, to interpret the book for you, and then hopefully you'll go back and read and get that more nerdy understanding if you must. Let's take a look at a problem with the formal definition real quick. Because I want to show you what's really happening graphically, okay? So what's the one we did last time? Did we do like 5x minus 3? What was the linear one we did on Wednesday? Anybody have that? Where I found the delta?
Add x minus 2 equals 13.
Okay, nice. So I just wanted to change it up a little bit, right? So I want to look at the limit. Let's say if 3x minus 1 is x goes to 2. Okay? So I know this limit. This is easy. I just find the height of this, right? And I'm plugging in. So since I can plug in, I plug in, right? So what do I get? 3 times 2 is 6 minus 1, I get a 5, correct? Everyone agree with this? This is easy to do, correct? Right? And of course, you'll never have this problem on the test because it's too easy. There's nothing to show me. But we know that this is equivalent to, right? For every epsilon greater than 0, there exists a delta greater than 0, such that 0 is less than the absolute value of x minus 2, right? I'm doing x minus c is less than delta, implies that f of x, 3x minus 1, minus the limit, minus 5, should be less than epsilon, right? Remember, I'm taking that formal definition, I'm plugging in the value of c, I'm plugging in the value of the function, and I'm plugging in the value of the limit, right? Right, everybody with me here? I can simplify this. For every epsilon greater than 0, I should be able to find a delta greater than 0, such that 0 is less than the absolute value of x minus 2, which is less than delta, implies it looks like I get, what, 3x minus 6 is less than epsilon. And now how I get this answer, how I get this delta, remember I have to find the delta, is I cheat. I look at this, and I realize I can factor out a 3, right? I look at the end result, and a lot of times it's easier when you're doing math if you don't know what to do, if you can look at the answer you can see, oh, look, there's an arctan in the answer, or there's a trig in the answer, or there's a, right? There's a factor of 3 in the answer. I can kind of, from that, work backward a little bit, right? So that's where I'm going with this, but you don't have to do that this semester. So I want to say, let epsilon bigger than 0. Pick me that bullseye, the dartboard or the target, and pick delta equal to epsilon over 3. You can see where I'm getting that 3 from. Look in that red circle. If I factor out a 3, what's left in the absolute value? If I factor out a 3 from that circle, from that red circle, what's left in the absolute value? X minus 2, right? And so you can already see that that's related to delta. X minus 2 and absolute value is related to delta. With 0 less than the absolute value of x minus 2 is less than delta, we must show that the function 3x minus 1 minus the limit is less than epsilon. But that's already almost done for us already, right? So we know that 3x minus 1 minus 5 is less than epsilon. The absolute value is what? 3x minus 6, which is 3 times the absolute value of x minus 2. Okay, but x minus 2 in absolute value is less than delta. So this is really less than 3 times delta. The 3's are the same, right? And the absolute value of x minus 2 is less than delta. But I picked the delta, didn't I? That's epsilon over 3. And now I can see that my 3's will cancel, and I get an epsilon. And look at what I get. I get epsilon is greater than the function minus L. That's what I wanted. If you don't understand that, I don't care. I want you to understand the next thing I show you, okay? So I'm opening up a program called Sketchpad. There's a version of this that you could find if you were really interested, or if you're a math major or a computer science major, on Desmos. You go to Desmos, you search for epsilon delta. So you can see here I've got a function. This particular function is x squared. I'm going to change it to our function. But you can see that AB is the radius of my my overall target, and AC is the radius of my bullseye. So A to B is my epsilon, right? And A to C is my delta. Okay. So I want to change my function here. What did I have? 3x. What did I have? 3x minus 1, right? And I got a value of 5. When x goes to 2, I got a value of 5. And so I said, let everybody with me? Everybody okay here? Right? So epsilon, I said let epsilon be bigger than 0, and I got that. And then I said let delta be epsilon over 3. So I'm just estimating right here. I've got about a third of the radius of the big circle for the smaller circle. And then what did I say next? I said make sure that the x's I pick are within the radius of the bullseye. So basically, I'm putting up, like if I'm going bowling with a bunch of little kids, which that would be the absolute hell for me. I'm going to put up the gutter guards, right? So I'm going to say let nothing fall outside of the width of that target. So I'm going to construct parallel lines here. What I'm interested in is I'm interested in that segment, and let me change it. Let me take the display. Let me take the line style. Let me make it thick, and let me change the color. I'm interested in making sure. So remember, I'm shooting arrows or I'm throwing darts at this target, and I'm making sure nothing can go outside left of or right of the width of my bullseye, right? That's my x minus 2 is less than delta in absolute value, right? And so I'm saying I picked epsilon over 3. Look at the piece of the function that's in between those guards, right? Isn't that completely on the big target? Isn't that orange strip of the function completely on the target? Yes. Imagine I pick a different delta. This is about here, delta over epsilon over 2. This one doesn't work because look at now that orange part of the function. In between my guards for delta, it's off of the top of and the bottom of the target. So that means I shot the arrow but missed the target completely. So when I make my target small, I still could have missed the limit. I still could have missed the center, right? Because remember, I'm going all the way down to 0. But you can see there's some orange that's off the top and bottom of my target. So, but if I pick epsilon over 3, you see how the orange is completely on the target? That means now, when I shrink this down to nothing, guess what? What did I hit? What did I hit with my arrow?
Bullseye.
The bullseye. The bullseye is infinitely small. So is the target. And I hit the target. Right? I hit the target. So I had to hit. So when I go to every single dartboard, even the one that goes to nothing, epsilon greater than 0, right? 0.01, 0.001, 0.0001, that radius, I still hit the center. I hit the bullseye. I got the limit. So that's what's going on. If I can guarantee to hit the target, right, then I guarantee that I'll get my limit. And that's what this thing says. That's what this formal definition says. It's not easy to understand. But I think the target piece is easy, right?
Professor?
Yes. No, yes.
In this instance, in this formula, which one is epsilon, which one is delta again?
On the screen here? On the screen that I'm showing right now? Epsilon is any positive number. Delta is a specific positive number, right? And I had realized, well, as long as I take 1/3 of my dartboard for my bullseye, I'll hit the board. And if I hit the board, I got the limit. Okay, let's talk about our next little piece here. Everyone okay? Can I move on? Anybody got a little bit more of an understanding of what's going on here, or anybody going, I'm dropping this class. I don't know what the hell's going on. This guy's speaking Greek. What the hell? Any clearer understanding? I got a couple notes.
Sketchpad helped out a bit.
Yeah, it's really valuable. In fact, like when I learned Calculus 1 in oh my God, what year was it? 94, something like that. I was doing everything on computers. So I really like the visual of things. And again, one thing you're going to do is when you have a function that you don't know what it looks like, graph it, right? Graph it. And it's going to be really mandatory as we go on. Some functions you'll have no idea what they look like. If you took this class at College Park or any University of Maryland campus, no calculators on exams or quizzes. But that doesn't mean you can't, when you're studying, look at functions on look at graphs on the calculator. It will help, and it will start to. By the time you're done with Calc 1, you should be able to basically get the sketch of any curve without a calculator. All right, let's talk about when do limits fail to exist, and then we'll look at some graphical limits again, okay? So D&E does not exist. I hate the fact that the book is going to have you do this. They'll say the limit as x goes to 0 from the right of 1 over x equals, and you're supposed to write in D&E. And of course, the equal sign means numbers, right? The equal sign means numbers, but the program is weak. I can't do anything about it. So, but I would rather you on paper write the limit as x goes to 0 from the right of 1 over x does not exist. I'd rather you write the English and the correct math, right? So you wouldn't write equals does not exist, right? You only would use that equal sign when there's an actual number. But it leads us to when do limits exist or not. Now graphically, this one's pretty easy to see, right? There's my 1 over x, right? And I mean, let's just pick a number, right? Let's just pick some number that you would want to say the limit is. Let's say, 5 billion, right? Yes. So 5 billion is what I'm saying that limit is. And you can see that if I draw this dartboard, right, you can see that there's a piece of the function above the dartboard, no matter where I draw that dartboard, because I could draw a dartboard of any size, the function is going to keep going up and up and up, right? Let me draw a better version of the function, like where it gets really close to the axis, right? So you can see inside of that blue, there's some function above the dartboard, right? Which means if I shrink it down even more, it doesn't even hit the dartboard at all. So our first case of D&E, right, is an unbounded function. Unbounded functions. And this particular example is perfect for it, right? There's no way I can draw any size dartboard and not have part of the function going off to the top or off down below if it's unbounded, right? And it's not, remember, it's not just one epsilon. It's not just one dartboard, right? It's everyone, even the one that's 0.00001, even that radius. So I have to be able to draw the tiniest of tiny dartboards and still keep the function on the board within my gutter bumpers, whatever they're called in bowling. So numerically, this is pretty easy too, right? Numerically, this one's pretty easy, yeah. Right? So like if I do x from the right and f of x, right? And I put in 0.1 and 0.01 and 0.001. What do I get, right? I mean, it's pretty sad that I have to use the calculator for this, but I can't. It's too early for me to be doing things. So 1 divided by 0.1, it's 10, right? And then 100, and then 1,000. You can see it's never going to stop, right? So no matter what number you think of, I can pick some x that blows past whatever value you're saying the limit is, right? In fact, we'll say the limit as x goes to 0 from the right of 1 over x is infinity, and that does not exist. Again, this is an issue with WebAssign. They're going to say, well, does it go to positive infinity or does it go to negative infinity? And because my limit is a number, and infinity is not a number, right? It's a concept. It does not exist. Okay, case 2. How are we doing here? We're fine with this, right? Yeah. So case 2 is a jump in the curve, right? A jump discontinuity. We don't mind a point discontinuity. We don't mind a hole in the curve. I still wouldn't want to ride that roller coaster, but the jump one is really bad, right? When we have some function that has a huge jump in it, right? This is a jump discontinuity where one part of the function is way separate from another. And even if it's just a point, we're okay with that, okay? But when I have, right, some jump, and it's easy to visualize that. So you can see here, if I pick my epsilon to be a half, no matter what size bullseye I get, you can see there's function above and below my dartboard. And this particular function that I'm using here, f of x, is absolute value of x over x. And I think I had mentioned this one last week, but there's lots of them. Again, read the book, right? This one's got a jump discontinuity. I think I even did this one numerically with the class, didn't I?
Not sure if we did that one, but now that you're showing ones where the dartboard doesn't work, the dartboard makes sense to use.
Yeah. And so think about what number I'm getting out of the right here, right? So if I'm looking at the limit as x goes to 0 from the right, right? If you think about that table, the absolute value is meaningless, right? This is really the limit as x goes to 0 from the right of x over x, which is just 1, right? No matter what x I put in, I get a 1. Right? Because when I'm putting in a positive number, absolute value is meaningless, right? Just take it off. Don't need it. And from the left, right? When I do the limit from the left, I'm going to get a negative 1, right? So when I'm going from the left, my absolute value of x becomes the opposite of x. It's just I'm taking the negative and turning it to positive. So I always get negative 1. And remember, I have to get the same. I have to be able to predict the height, right? And I can't without me knowing which side I'm on, right? So I can't. I can't tell if I'm going to a height of 1 or a height of negative 1. I can't tell. But the epsilon, the circle should make the most sense here, right? I mean, the table's easy too, right? But when I put the epsilon in, any epsilon, in fact, every epsilon, if I put one in that's in between the pieces of the curve, I have to have curve off the board. If I have a curve off the board, when I shrink it down to almost nothing, it's still off the board. I miss the limit.
Professor, so any points that's within the parallel lines when strings should hit the bullseye.
Yes. Yeah. So if I picked this guy as my epsilon, you can see the pieces highlighted in my green highlighter there that are on the function are on the board. Okay, that's good. But the problem is, if I pick a smaller epsilon, no matter how big I pick for the bullseye, the pieces of the function within that restriction of absolute value of x minus c is less than delta are not, that's not on the board. So when I shrink it down, those arrows that miss the board still miss the board. No limit. The last one is the most interesting, but also easy to see. And again, you're gonna be graphing things. We're talking about an oscillation. So let me just jump to a new page because I'm getting a little zoomy here. DNE case 3. An oscillator. So the old joke is like go down into grandma's basement and there's a light with a string on it, right? Can you see that? So I pull the string, the light goes on, and pull the string, the light goes off, pull the string, the light goes on, right? And if I do that an infinite number of times, is the light on or off? What is it?
It's not defined.
It's actually off because the light will burn out.
Well, okay, yeah, sure.
It's a joke, but yeah, it's when I'm oscillating between 2 points, is it really clear where I'm going to be at the end? No, right? And so I like to look at the function f of x equals the sine of 1 over x. Now it's hard to see what this thing looks like, so I'm going to graph it because that's what I want you to do. When you see something that you don't really recognize, right? We want to put it in a calculator. And there's nothing wrong with you using Desmos when you're practicing, but you better make sure that you practice on your calculator as well. So I'd like you to probably do both. So you go to Desmos, and you'll get a better picture, much more powerful than these dinosaurs we carry with us, these TI-84 sauruses. So y equals sine of 1 over x. And you can see my oscillation happening. The best part about this, especially if you have a screen where you can zoom it out, right? You can really see this oscillation happening. It's just going nuts in between, right? If you think about it, the frequency. Do you remember in pre-cal you talked about frequency modulation and amplitude modulation? This is frequency modulation. And so what we're saying is the number of times it goes around the circle within 2 pi, right? And so think about 1 over x. If that was my frequency, as x gets smaller and smaller, that number gets bigger and bigger. That b value gets bigger and bigger. Does this make sense at all, what I'm talking about? This frequency modulation? And so as this x gets small, this point moving around the circle is going so fast, right, that you're getting these heights anywhere between -1 and 1, everything in between, right? And so you can really see on this picture, it wouldn't matter where, if I pick an epsilon less than 1, right, I'll always have, you see how dense it is at 0? I'll always have values above and below above my dartboard here, right? I'll just try and see if I can draw it on here. Can I draw it on here? Let me see if I can draw on here. Share graph, no. Help, no. No, I don't know if I can draw on here. Can I? Nope. Let me just draw it real quickly here. So, right, I know it's going nuts here between -1 and 1, right? And I'll pick a dartboard, I'll pick a bullseye. You can see above and below, right? There's some values. There's always going to be some values of the function above and below the board, right?
Does the frequency of the function like approach to infinity as you go to 0?
Yes, exactly.
Okay.
Infinite. So that's what makes it
So
really
at 0, it's just everywhere.
exactly,
Basically.
exactly. It's so dense. In fact, at 0, there's a hole in the function, but I don't know where even to put the hole. Right? I don't even know where to put the hole. Right? Because it's just so dense. Right? It's going so fast. It doesn't even look like there's a point moving around the circle anymore. Right? It's going so fast I can't see it. This one's a nice one to see numerically. Right? Graphically, very easy, but numerically, this is a nice one to see. So I want to go x from the left and x from the right and f of x. Oh, I don't know if I want to do that, but let me just do from the right first. So let me do this on my calculator on the screen here. So you can go along with me. How am I doing on speed today? Am I going too fast? Everyone's okay? Nice.
This part's fine. Maybe earlier was a little bit fast, but this part's fine.
Oh, with the epsilon part?
Yeah.
Yeah, I didn't care how fast I went there because I don't care if you get that, right? But if you get the dartboard, I care. That dartboard is what I need to do this part, right? I need to be able to have you visualize that I can have some of the function off the board. That's all I need, right?
Yeah, that's
Nice. So I want sine of 1 over x. Go ahead.
Yeah, on the test, do we not have to prove using the epsilon?
No, not on the test.
Okay.
I'll put it on you. No, Nahum, if you want it, I'll put it on yours if you want.
Nah.
Okay. All right. Okay. So I remember what I did here. I got my function in sine of 1 over x, right? I want to look at the table set. I want to make sure I put my table set on ask. There's another way to do this. I can have it generate a whole table for me, but I like to be in control a little bit. I like to pretend I'm in control. And then I'm going to second table. Is anybody doing this with me along right now? Okay, so we're okay. Where I'm at, nice. So I got the function in. I make sure I put my x value on ask so I can type in, and then I go to my empty table, right? Anybody need a minute? And I have my chat open. You can always chat to me if you don't want to say it out loud.
What did you do after you hit ask?
Yes, so I'm in y equal, right? I got the function in. Then I go second table set, and I go down and make sure I hit enter on ask. So that's now highlighted, right? And then I do second table. That's now my table. That's where my table is going to get generated. And if I did this on my exam or homework, I would just be copying this table onto the page. There's no work to show. You don't have to show me. You can plug in numbers to a function. I know you can. So I want to look at I'm going to look at my positive value and my negative value at the same time. So I'm going to look at 0.1, that's from the right, and negative 0.1, that's from the left. And remember, sine is an odd function, right? Sine is symmetrical to the origin, right? So I'm going to get a positive value on the right and a negative value on the left. And that's going to keep happening. And guess what? They're going to start to switch, right? And that's going to keep happening. So you're going to see the oscillation in my table. And this one's weird because gas station money doesn't give me an answer anymore. But I can already see I've got not the same height on left and right. So let's do 0.01 and negative 0.01. And again, you can see I get the same values, but opposites, right? Because sine is odd, right? So 0.001, negative 0.001. All right, well, at least it got away from 0.5. Now I'm at 0.8, right? But still, so you can see I'm moving toward positive 1 and negative 1. And then I would just switch. And it's just going to keep happening. And so even though if I stop here, I can say, oh, they're not matching, right? But I have to be careful. So for example, if you do numerically, and I would ask you to do that. Oops, sorry. Not supposed to show that. If I did numerically g of x equals cosine of 1 over x, that one's really tricky because the table will match everywhere, but it'll never settle. It'll just keep going up and down because cosine is an even function. So I'll get the same value from a positive or negative, right? So cosine will just keep doing this and matching. Nice. So we looked at when do things fail to exist, right? So we talked about this now, but I want to go back to graphical limits real quick and just do one or two of them.
Oh, Professor.
Yes.
Tell me if, just let me know if you're going to teach us later, but really quick, how do you know if a function is continuous? Because
a function's continuous if there's no hole in it. If it's a roller coaster you would like to go on, right? So this particular roller coaster will just hurt a little bit, right? But this one,
right,
would hurt a lot, right? So on the first one, on the highlighted in blue, I'd feel probably a little bump. Hopefully the tires are bigger than the hole, right? It's like going over a pothole on that one, right? On the other one, big jump. So
right.
Both are not continuous. But what's interesting is the blue one, the limit exists. The red one does not exist, right? So on the red one, you can see that jump discontinuity. And the other one,
okay.
I just have a point discontinuity. And the limit in the blue one exists, right? And that's where we're getting to. We want to be able to find... We want to be able to ski down the hill. This is a bigger picture here, okay? I want to be able to ski down the hill. And any point on the hill, right? So here I am skiing on the hill. I got my headphones on. Any point I would like to be able to calculate the slope of my skis, right? And this is called the derivative function. It tells me the slope at any single point, right? And so if there was a hole in the hill, I couldn't stand there. I'd fall in. So I couldn't get the slope of my skis, right? So it's easier to find this derivative. In fact, it's only possible to find the derivative when the function is continuous. So we're starting with limits because that's going to help us get derivatives. But you'll see that we're doing a little piece in between called continuity because I need the continuity to stand on the hill to be able to calculate the slope of my skis. And
right.
It sounds really weird, I'm sure, to a lot of you, but you'll get, when we get there, you'll get it. All right, let's look at a couple of graphical limits exactly to this point that we just talked about here, this continuity point. So I want to look at C, and I'll pretend that every tick mark is a 1, right? I want to look at C that doesn't match up with my curve. So this is f of x, right? So I want to look at here, the limit as x goes to C, x goes to 2 of f of x, right? And so the question is, well, the books and the web assignment will ask you several questions here. They'll ask you, what is the value of f of 2? And what is that value there? F of 2 is what height?
Peony, because...
Nope.
2.
2, yep. So it's like I've got the cover of a manhole in the road off to the side, right? So it's like, where's the hole in the road and where is the cover for the hole in the road kind of question. This is called a removable discontinuity. Okay, we're not there yet, but we will be. And so then they'll ask you, what's the limit as x goes to 2 from the left? So as I'm walking from the left toward that hole in the road, what height am I walking toward? What height am I climbing up to? It's obvious. 3. And what about the limit as x goes to 2 from the right? What height am I walking toward? Again, 3. So since my limits left and right match, I know that the limit as x goes to 2 is 3. Even though there's a hole in the road there, right? Even though there's a hole in the curve, it's not a jump, right? And so think about it. For every epsilon greater than 0, there exists a delta greater than 0 such that 0 is less than the absolute value of x minus c is less than delta, implies that I'm still on the curve, right? I'm still on that safety zone around the hole. And this is the key that says I don't care about the hole. I don't care about getting to 2. I only care about getting close enough so that I can predict the height, right? X equals 2 is not important to me when I'm doing limits. X equals 2 is important to me when I'm doing continuity. X equals 2 is important to me when I'm doing differentiability. Okay, but not when I'm doing limits. So I'm kind of baby stepping up to differentiability, finding the slope, right, at the one point. If the point doesn't exist, how could I find the slope there? I can't even stand on the hill, right? There's an interesting limit on Google.
Professor, I have a quick question.
Yes, talk to me.
So I remember there being like when those questions like came together, the limit from the right was one thing, the limit from the left was another. So the limit exists, but then the value at like x equals 2 didn't exist, right?
Oh, sure. If I did the same problem, right, and I just took that piece away, right? So, and I said f of 2 does not exist. I don't care. I don't care if f of 2 doesn't exist because
You just want the
I just want the height. Yeah. I'm not saying climb all the way there. Once you're within gas station numbers, you should be able to predict where you're going without ever getting there. It's weird. It's a weird concept, but you'll see the value. You see the value in it already by me coming up with that replacement function that I could just plug in. Right? That replacement function allows me to fill the hole. Right? Put that manhole cover back on the road so that no one steps on it and falls in, kind of thing. Here's my Google. Here's my Google search here. I'm going to search for 0.1. And so Google's telling me there's 3,230,000,000 results here, right? Just for that string or number in a web page, right? So So then I want to search for 0.01. I had 3 billion. Now I have 4 billion. I have even more. But I don't care about oscillation early. So now 0.001, 6 billion. It's still going up, but it's here at 298 million. And you can start to see that I'm going to start to go down pretty consistently. 18 million results. Yes, you with me? Yeah? So I'm searching for the string 0.0001 in web pages, right? And I got 18 million results. Next one, 16 million results. right? Let me just jump ahead here because they keep going down, right? 127,000 results. Where am I going to? What's my limit here? Do you know? As what I'm searching,
it's approaching zero.
it's approaching zero, right? So as I'm searching for the number that's getting closer to zero, I'm getting closer to zero results, right? And so I can just go a little bit more crazy here and search for something really close to zero. 32,000 results. So it's pretty clear that as I'm doing this Google search, I'm going to get closer and closer to zero results, right? But what's funny is if I search for zero, 4 billion. So there's that single point that jumps, even though the results are going to zero. When I actually get to zero, which I don't care about doing, it jumps back up to right a lot of results. But the limit is still zero, because I don't want to get to zero. I want to get close to zero. It's kind of a joke, but still.
It's funny that actually works
Yeah,
for
yeah.
Googling.
Yeah. Okay. Where do we have to go? Let me look at my list here. I think we're ready to do the secant tangent problem. And what time am I done? I forget what time our class is.
30 minutes?
Yeah, 9:40, right?
9:25.
9:25. Thank you. I tried.
Yeah, the
tried.
5 minutes to 9:30 would be our time to walk to class.
Right. So secant tangent problem. I think I'll get this done, and if I don't care. But you certainly can look at homework 4 after today. So homework 1, 2, and 3 are from 2.2. Algebraic limits, graphical limits, numerical limits. And then 2.1, homework 4, and I jump around on purpose because 1, I get bored, and 2, it makes more sense for me to do it this way, is the secant tangent problem. So 2.1 or homework 4, the secant tangent problem. Now I'm going to do something on Desmos today, what I like to call a dynamic secant line. I'd like you to try and do that. And I may ask you to send it to me eventually. So you would go into Desmos, you'd create a login so that when you create a sketch, you can save it and share it, right? So it might take you a couple times to get what I'm going to do today on Desmos, but we'll see if you can do it. The whole idea here is that I have some function and I'm interested in the tangent line. I'm interested in this slope, right? I'm interested in that slope of the line that hits one time. This is called a tangent line. So the tangent to a circle would hit the circle once, right? A secant hits a circle twice, and a secant line, right, which will make a lot of sense to us, and it's easy to calculate this. This is in purple. My secant line, it's easy to calculate this slope, right? It's very easy to calculate the slope because I have 2 points. And I'm going to pick those points as x and x plus h. So the distance between here is h. The distance in the x direction between my 2 points is h. Oh, and I screwed it up already. Sorry. Let me put my tangent line on this point. Sorry. It's easier for me to think about the tangent line at that first
You'll
point.
have to deal with negatives.
Yeah, exactly. H. I want to keep h to be positive for now. We'll let h be negative later. So just to try and get a little bit of a better picture here, don't change anything on your picture yet, okay? I want you to see that this tangent line, I'm really only connecting once to the black curve. Yes, it's crossing it later, but I'm only interested in, remember, that tiny little delta or epsilon value, very, very small, right? But again, I still can see my secant line going through 2 points. And it's very easy to calculate that secant, right? So I want to think about my points here. This is the point x comma f of x. And this is the point x plus h comma f of x plus h. Right? y2 minus y1 over, right? All of that. So anyway, the slope is going to be f of x plus h minus f of x all over x plus h minus x, right? This is the slope of my secant line. So I'll say m sub sec, slope of the secant line, right? y2 minus y1 over x2 minus x1. And then I can simplify that a little bit, right? F of x plus h minus f of x. And what happens downstairs, the h's just cancel. Sorry, the x's cancel. And I get the slope of the tangent line when I let the limit as h goes to 0 of f of x plus h minus f of x over h go to 0. And this guy is called f prime of x, which is the derivative. The derivative will give me the slope of the tangent at any point on the curve. And you see how I get it, I get a limit, right? So this is why I do limits first. I want you to be able to do this limit. So what the book is going to have you do, what WebAssign is going to have you do, is going to have you calculate a bunch of secant slopes, right? So imagine I pick a second one, and then a third one, right? And you can see my blue slope to the green slope to the purple slope to the red slope. They're getting closer and closer to each other, right? Those secant slopes are getting closer to the tangent slope. And so what the book is going to have you do, what WebAssign is going to have you do, is calculate secant slopes and then guess for the tangent slope, right? Calculate secant slopes and guess for the tangent slope. That's a limit, right? And what I'm going to have you do is calculate the tangent slope, right? All right. Maybe some confusion here. Talk to me. What are we seeing? Anything weird here on the page?
I have a quick question. So,
yes, soon. No problem.
Yeah, I'm trying to trip it all together. So as the difference between x and x plus h becomes 0, or like approaches 0, the slope also becomes 0, but that
no, the slopes get closer to the slope at one point. Right, and we're all going, you can't calculate a slope with 1 point.
Mm-hmm.
What are you going to get? 0 over 0, right?
Yeah.
If you think about your 2 points are the same point, y2 minus y2 or y minus y over x minus x, you get 0 over 0, right? Mm-hmm. And so that's the beautiful thing is I can't calculate the slope at 1 point, but I can at 2. So I keep calculating the slope at 2 points as they get closer together, and then I can predict what's going to happen at the 1 point.
So, like, the value will be, like, close to 0, right?
No, it could be any. So if you think about this slope that I have here on that red line, I mean, maybe it's 1, right?
Right.
But the purple line is less than 1. The green line's closer to 1. The purple line, they're getting steeper. They're getting closer to the steepness of the red line.
Right.
Yeah. So it could be any slope at that 1 point. We don't know, but by the time I get the gas station money, I'll be able to guess. Okay. By the time I get to the third secant line, I should be able to guess. is what's going to happen in all these problems. So let me just jump right to a problem. So this is just like the second problem in your WebAssign work, okay? I'm not going to do my dynamic secant line today. I'll do that Wednesday, okay? So I want to look at this function f of x equals x over 1 plus x. And I want to find, and so by the way, if you don't know what that looks like, you certainly could graph it, right? You certainly could graph it, but I see a horizontal asymptote at 1. I see a vertical asymptote at -1, and I get some kind of value, some kind of function like this. And I'm interested in the point at 1/2. I'm interested in 1, 1/2. First of all, if I plug in x as 1, you agree I get 1/2, right? So I'm really interested in that tangent line. Not only do I want the slope at that tangent line, I want the not only do I want the slope, I want the equation of the line, right? And so that's something that, you know, a lot of us will have a little bit of a panic on, I think, once we start doing equations of lines again. If you remember doing those in the past. So what I'm going to do is I'm going to approach this from a bunch of points to the right, right? So I'm going to get this secant line, or a bunch of points from the left, right? So again, I'm going to do exactly what the book is going to do, but I'm going to do it a little bit different, a little bit more sophisticated, because you already know how to find limits. So let's look at the slope, right? What's the slope? I need, so my fixed point is going to be 1, 1/2, and my arbitrary point is going to be x, f of x. So I need f of x minus 1/2 over x minus 1. Right? So think about it. Let me just try and draw the picture a little bit different. This is my point 1, 1/2, and this is my point, arbitrary point x, x over 1 plus x. And I'm doing the slope there, right? So y2 minus y1 over x2 minus x1. And of course I can put the y2 value in, right? We know the function is x over 1 plus x minus 1/2 over x minus 1. Is everybody okay here? This is the slope of my secant line. Anybody? And I have my chat open. Everybody okay? Nice. Well, I know how to deal with this, right? This is fractions within fractions. I know how to deal with this. By the way, this is the difference quotient, if you remember that from pre-cal, right? This is my slope of my secant line, difference quotient. Difference meaning I'm subtracting upstairs and then dividing, right? Difference quotient. So I know I need a 2 times 1 plus x here. Over itself, right? I get the interior denominators as my LCD, right? And so this is my secant slope still. So I get 2 times x times a 1 plus x over 1 plus x. I'm distributing through here. Minus 2 times 1 plus x over the 2. And downstairs I'm not going to do anything, right? 1 plus x times x minus 1. And of course you can see where I'm interested, the limit I'm interested in here, right? You can see the limit I'm interested in is what? X is what? Not 1/2.
Oh, okay.
Look at that denominator. What point is the point of interest? for that original slope there. Where's my point of interest there?
At 1?
At 1, exactly. Remember, I want the slope at 1, but I can't figure out the slope at 1. I need 2 points. So, but this is going to help me get the slope at 1 point. All right, a bunch of things cancel here, right? The 1 plus x's cancel, the 2's cancel. I'm not in a rush. I'm Polish. I'm not Russian, I like to say. But even if I was Russian, it would still be funny. I'm Russian, but I'm not Russian. So I'm trying to simplify as much as I can without doing too much. So it looks like I can distribute upstairs. I get 2x minus 1 minus x. And so my 2x minus x simplifies to just x. Ooh, look at that. It's pretty magical what happens in these. Right, you see my x minus 1s are going to cancel, right? So right now this is still the slope of my secant line. For x being 1.1, 0.9, left and right of 1, right? And so the book is going to ask me for that. The web assignment is going to ask me, plug in 0.1. But these are going to cancel anyway, so I could still plug in 1.1 here and calculate a secant slope. I can plug in 1.01 and calculate a secant slope. I can plug in 1.001 and calculate a secant slope. And then make a prediction. But guess what? I can do, this is the slope of the secant, right? Is the value of 1 over 2 times 1 plus x. But the slope of the tangent is the limit as x goes to 1 of 1 over 2 times 1 plus x. But guess what? I can just plug that in. I get 1/4. So you'll see my secant slopes are going to get closer and closer to 0.25. My tangent slope is exactly 0.25. All right, so in homework, I'm out of time. In homework 4, which is from 2.1, they're going to ask you to calculate a bunch of secants and then predict the tangent. They'll do that even when they give you the function like I have, but you know how to calculate the slope of the tangent by doing the limit. So do it my way, do it their way. Do both. Yes, no.
Go ahead. No, go ahead.
No. I was just going to say goodbye, but go ahead.
Okay. So basically what we do is we find the slope of the secant line, which also results in the the limit of the tangent line.
Exactly. You'll be able to, if you keep doing secants closer and closer, you'll be able to predict the tangent line slope.
Wait, when you mean closer and closer?
When my points move closer and closer together, the secant slope will become the tangent slope.
Okay. So
and I'll give a nice visual of that on Wednesday. Right now, just be robots. Calculate secants. Calculate the next secant. Calculate the next secant. Where do you think it's going? Right?
Okay.
Just be a robot for now.
Also, after we find the slope of the secant line and the limit, we can't find limits also, and then that we have to find the replacement function, right?
Exactly, which I did, which I just did.
Okay.
Right, and it turns out that this replacement function came from a slope formula. Right, the replacement function came from y2 minus y1 over x2 minus x1. Right. All right, I'm out of time. I don't want to keep you late. So do your best. It's okay if you don't get it right away. I'll see you Wednesday.
Professor, I had a quick question.
Yes, of course. Up soon.
Said you assigned a homework due Sunday at midnight. Do we still have more to learn before that's assigned, or like?
No, the first homework will be limits. It'll be from homework 1. The first homework assignment will be from homework 1. Just I will make up new functions.
Okay, thank you.
Yeah.
So you're going to give us those questions
So I'll give them Wednesday.
Okay.
Yep.
Have a good one.
Thank you, Professor.
Thank you.
Thank you, Professor.
Have a nice day.
Thank you.
Have a nice day. Goodbye.
Thank you.
Carson, you received my letter, my disability
Yes,
letter,
and I responded to you.
because I didn't look like my email last week. Okay.
Yeah,
Thank you.
I responded to you like 5 minutes after I opened it, which was right away.
Oh.
It says because
Okay.
we're in private now. It's just you and I here. It says
Oh.
that letter is only good for fall 2021.
Yeah, 2021 is, yeah, 2021. Okay, yeah, you will ask for a new one.
Yes,
Okay.
exactly.